I got enough people in one grade ahead.
So we're going to backtrack just a little bit. Not ready now. Okay. Backtrack a little bit into lesson 6. In lesson 6, we introduced the concept of the derivative being an instantaneous rate of change, or essentially the slope at one point. I'm going to write some of these things down as I'm saying them. If you want to write them down, you can. It's up to you. So if we just kind of, like I said, sort of a summary, we identified this thing called a derivative, okay, which was an IROC, an instantaneous there we go, rate of change. Or sometimes we talked about it, it's the slope of the tangent line to the curve, because it's the slope or the rate of change at one point, or at one point in time. Okay. Different from an algebra slope, which was an average rate of change, or the slope between 2 points. So in calculus, we make a big deal, it is a big deal, to study the rate of change of a function at a single point. We call the measurement of that rate of change the derivative. We've looked at two different limit calculations that will yield a derivative function. If you use them one way, they'll yield a derivative value. If you use them another way. We're going to talk today about how to come up with derivative values and derivative functions without having to go through the limit process, which is really nice. But there are times where we can still maybe talk about a derivative value or a derivative concept, a slope at one point, an instantaneous rate of change that has a totally different presentation of the data. That is the data given in a table. Okay. We've already looked at, when we looked at this table earlier, let's scooch down here. This is in your packet. So on the first page of the packet, we looked at this table, and we used this table to calculate an average rate of change, AROC. As weird as it's going to seem, we can also use table data to calculate, or not calculate, but estimate an instantaneous rate of change. So, let's look at this type of problem. Given this data below, estimate the instantaneous rate of change in the revenue of Under Armour in 2007. Now, a couple things. First of all, the vocabulary here. Instantaneous rate of change tells you this is a calculus question, not a algebra question. Actually, the fun thing is that we're going to use algebra to estimate it. And we're only looking for the slope at one point. Okay. The way we're going to do that, however, is 100% because of the relationship between an average rate of change and an instantaneous rate of change. That secant line slope can be turned into the tangent line slope by just some movement if I want an instantaneous rate of change, or at least an estimate for an instantaneous rate of change, I can use an average rate of change close to, and in this case, I'm going to say close to 2007. If we talk about an average rate of change sort of around or across 2007, for example, maybe from 2006 to 2008, that average rate of change is a good option for an estimate of the instantaneous rate of change in 2007. Okay. So essentially I go across it. I say, all right, so what's the change from 2006 to 2008? And the change between those 2 points can be a reasonable estimate for how things are changing at just this one point. Average rate of change to estimate an instantaneous rate of change. So if I look at my 2006 data and my 2008 data, I can take I am done with red marker today. Let's use green. Okay. Let's take this data and this data. So 780 minus 420 over 2008 minus 2006. 16. About 360 over 2, or 180. So if we wanted to write something about that answer, that is 180 million per year is what we're estimating is the estimated, in this case, increase in the year 2007. From 2006 to 2008, it's increasing at about 180 per year. So if I wanted to say, well, what's happening in 2007, we could say it's probably increasing at about 180 per year at that point. The slope across that point in time can estimate what's happening at that point. If we think about it sort of in a data process, in a graph, and this was the 460, and this is the 600, and this is the 720. It may not be lined up like that. Let's do like that. Okay. So this is the 2006 value, this is the 2007 value, and this is the 2008 value. What I want to know is, what's the slope right there? Just at that one point. What I can do is, I can say, well, let me use that slope. The slope from here to here will estimate that slope. Yes?
They're all on the same line though, because you add 180 to 420 and 600, you add another 180 to get 70. So the slope would be the same.
Yes, so in this case they are evenly spread, so it's kind of nice, but they don't have to be like that. So even if this were 680, that would still be considered a reasonable estimate.
Oh, okay.
Okay? That's a good point. So even if we don't have a context, even if it doesn't like talk about anything, we've still seen this kind of question. College Board has asked us, hey, estimate f prime at 4.3 from this table. Okay, so that means we want to estimate the instantaneous rate of change at 4.3. Any 2 points around 4.3, one on one side and one on the other, can provide an estimate. But if we want the best estimate, we get as close to that x value as possible on either side. So if I wanted to estimate the average rate of the instantaneous rate of change at 4.3, I would use this average rate of change. I would say, all right, 4.6 minus 1.8 over 4.9 minus 3.7. And whatever that calculates out to be, I'm not going to worry about that right now. 8 over 4.9. Sometimes in a problem like this, and this is the part that's really crazy. If this were a question and you had a calculator on the test, you'd be expected to finish it. You'd be like, okay, yeah, you should be able to finish this and get a final answer. If this was a non-calculator question and a free response question, if you stopped right here on the AP exam, that's considered sufficient. Any answer that's calculator ready, which basically just means all you would have to do to finish it would be to type stuff in the calculator, type arithmetic in the calculator, doesn't have to be finished if you're not given a calculator. College Board is going to say, we're going to accede that you would be able to finish evaluating this. The calculus in this question is understanding that when I ask you to estimate that this will do it. I don't need you to finish it. At least that's the College Board theory. You don't need to finish that to show that you understand the calculus. Okay. So something like this, perfectly legitimate just to leave like that. It's even weird sometimes we'll leave things unfinished, uncalculated, but we'll still throw units on them. Another part of working with the derivative, before we get into the new stuff today, this is kind of the last thing, so we want to make sure we understand how to describe what the derivative is measuring. So when you describe what a derivative is measuring, okay, first thing you should talk about is the sign, and are we representing an increase or a decrease? We need to have of units, so something per something at and we have to specify the 1 point in time when that's happening. Okay. So the verbal meaning of this derivative statement. Couple things. This is a negative value. So this derivative statement represents a decrease. It's the decrease in what? Read this problem. What are we measure? What is that? What are we talking about measuring as our output? degrees Celsius, so a temperature. So an increase or decrease in the temperature. So this is a problem about temperature. In, how would you describe the units? We've got the degrees Celsius. Degrees Celsius per day. Yep. And that piece is going to help you figure this piece. So the specifics of this problem, this is kind of like a generic, right? This is a good template for talking to me about a derivative. What is the derivative measuring? It's measuring either an increase or decrease in something with these units at this point in time. So the best answer for problem number 6, when you write this out to get full credit for explain to me what this derivative statement means, there's a couple different ways you could say it, but let me write this again. So p prime of 6 equals negative 1.35. As I could say, there's a decrease in temperature of, and this is tricky, 1.35. When you say decrease, that makes it negative. So you don't write another negative down. The decrease takes the negative into account. The decrease is in temperature of $1.35, 1.35 degrees Celsius per day at 6 what? At 6 days. At the 6th day, or at 6 days, or day 6, or something like that. Or on the 6th day. You can phrase this any way you want it, as long as you include all the essential elements. When is it happening? What is happening? So on the 6th day, the temperature is decreasing, and the decrease is 1.35 degrees Celsius per day. Most common mistakes: not putting the per day, not putting when it's happening. And a lot of times you're like, well, it's redundant. It's not redundant. This is the point in time. This is the unit measure. These don't necessarily always go together. Okay? They can't. They mostly do, but they don't have to. So you have to specify how the units are being measured and when the measurement is taken. On the 6th day, we calculated the temperature was decreasing at a rate of 1.35 degrees Celsius per day. It's decreasing how often? It's decreasing this much per day. All right. Those are all the sort of easier, fun things.